Look deep into interstellar space, into active star-forming regions like the Carina Nebula, and you'll find a universe organized by mass. This diagram maps the cosmic mass spectrum. For decades, astronomers relied on a strict boundary line drawn right here, exactly 13 times the mass of Jupiter. Anything below is categorized as a planet. Anything above is considered a brown dwarf, a failed star. To put that threshold into perspective, here is Jupiter. It contains more than twice the mass of all our other planets combined, yet it serves as the baseline measuring stick, a mere fraction of that strict 13 mass limit. That 13 mass limit gave astronomers a rigid rulebook for categorizing the universe. It worked perfectly, until we found an object that broke the rules. Meet 29 Signi B. It is a young exoplanet sitting 133 light-years away, radiating intense heat from the violent process of its own creation. Measurements reveal this world weighs exactly 15 times the mass of Jupiter. That weight places 29 Signi B securely past the 13 mass boundary. It occupies a cosmic no-man's land, an object with the mass of a star found in the territory of planets, which leads to an architectural paradox. Did this massive object collapse into existence all at once like a star, or was it built piece by piece like a normal planet? Stars typically form through a process called top-down collapse. Massive patches of interstellar gas and dust rapidly cave in on themselves under their own extreme gravity to form a dense sphere. Because 29 Signi B weighs 15 Jupiters, mathematical probability dictates it formed exactly this way. Planets, however, use a bottom-up process called core accretion. Tiny bits of rock and ice slowly collide, gradually clumping together over millions of years to build a solid planetary core. The problem is that bottom-up construction has mathematical limits. Eventually, the core simply stops growing. Standard core accretion models fail to explain how a planet could ever gather enough surrounding material to reach 15 Jupiter masses. So, 29 Signi B presents a physical contradiction. It is too massive to be built like a planet, but, as we're about to see, it doesn't behave like a star. To figure out how 29 Signi B was made, astronomers turned to the near-infrared camera aboard the James Webb Space Telescope. The first piece of data they pulled was its orbit. The gas giant sits a massive 1.5 billion miles away from its host star. If you overlay that distance onto our own solar system, it perfectly matches the orbital path of Uranus. It maintains an incredibly wide, stable, and perfectly aligned orbit. This alignment matches the rotation of its host star, suggesting the world was born within a swirling protoplanetary disk, rather than forming independently from a collapsing gas cloud. The orbital path confirms a planetary origin. But we are still facing a contradiction, a world born in a disk that somehow reached a mass previously thought impossible for planets. 29 Signi B is not alone. It is the primary target in a James Webb program designed to investigate 4 young, hot, and unusually massive exoplanets. To crack the mass paradox, the team shifted their focus. They stopped measuring the planet's orbit and peered directly into its 1,000 degrees Fahrenheit atmosphere. What they found were high concentrations of carbon dioxide and carbon monoxide gas. This chart compares elements heavier than helium, or metals. 29 Signi B's metal count spikes 150 times higher than Earth's. By absorbing metal-enriched clumps from its host disk, this massive influx allowed the planet to bulk up well past the normal limits of core accretion. 29 Signi B proves that the universe is highly capable of engineering supermassive worlds using purely planetary mechanics. The dividing line between stars and planets is defined by how a body is built, regardless of its final weight. 133 light-years away sits 29 Signi B, a massive world weighing in at roughly 15 times the mass of Jupiter. Its sheer bulk implies it collapsed from the top down, the same way a star is born. But its wide orbit, sitting about as far from its host star as Uranus is from our Sun, points to a slow, bottom-up planetary accretion. Without a clear categorization for this world, the line where the planet category ends and the star category begins remains dangerously undefined. Astronomers realized that size and distance were only part of the story. The real answers were likely locked within the chemistry of the planet's atmosphere. They turned to the James Webb Space Telescope. Using its near-infrared camera, researchers set out to scan the light radiating from the young, hot planet, looking for the molecular building blocks of its formation. That light carried a specific chemical profile, a direct link to the environment where the giant was born. JWST observed 29 Signi B, capturing the spectrum of light passing through the giant's outer layers. Molecules in the atmosphere absorb specific wavelengths, leaving distinct gaps in the data. This chart shows specific wavelengths of light absorbed by the planet's atmosphere. Those dips represent the presence of carbon monoxide and carbon dioxide. In astronomy, any element heavier than hydrogen and helium is a metal. Carbon and oxygen are the primary markers here. By measuring those molecules, the research team found that 29 Signi B is enriched with 150 times more heavy metals than Earth. Comparing the proportion of heavy elements, the planet is vastly richer in metals than the star it orbits. If both collapsed from the same uniform gas cloud, their chemical ratios would be identical. Instead, we see a massive discrepancy. This chemical mismatch indicates the gas giant gathered its mass by sweeping up solid clumps of rock and ice, the hallmark of planetary birth. While the chemistry builds the case for accretion, the physical geometry of the system offers a second, independent line of evidence. Researchers precisely mapped the planet's billion-mile orbital path. Then they measured the spin of the host star, locating its rotational equator. The 3D model shows a specific alignment. The giant planet's orbit matches the parent star's rotation. This alignment is the geometric signature of a flat, rotating protoplanetary disk. It confirms the planet grew within the disk of debris left over from the star's formation. The combination of mismatched chemistry and perfectly aligned geometry effectively rules out the star collapse theory. The evidence places 29 Signi B firmly in the planet category, an overachieving world built through accretion. This finding demonstrates that the bottom-up process of clumping rock and ice is capable of producing worlds far more massive than previously thought possible. It reveals a Milky Way where microscopic dust and debris can stack up to form the largest titans in the galaxy. The same incremental accumulation that built the rocky ground we stand on is also responsible for engineering these 15 Jupiter-mass giants. Nature can manufacture giants without the need for a violent collapse. Given enough material, the slow grinding